All right, I thought I'd give an overview about methods for handling missing data. So first, I have a few preliminaries. I'm going to tell you what I mean by missing data. I'm going to define the term, and then talk a little bit about what made the missing data, the missingness mechanism, which is sort of a fundamental aspect of any missing data method, and then what are the properties of a good method for handling missing data? Then I'm going to talk about main approaches to handling missing data, maximum likelihood of Bayesian methods, complete case analysis, which is just to discard any of the cases that have missing values, and weighting, which is a variant of complete case analysis, and also some hybrid methods, which I'll discuss. Then multiple imputation, which is one of my favorite methods for handling missing data. I'll talk a bit about robust approaches to handling missing data, and then what to do when you have data are missing not at random, as I'll define in the first pass. Since we're at Dana-Farber, I thought you might be interested in missing data in clinical trials. So I put in a section on missing data in clinical trials. I actually gave this talk to an education conference about a couple of months ago. And so I was talking about educational applications. So I excised the educational applications and incised the clinical trial thing. So one of the things that's fun about missing data is you can apply in lots of different areas. So if you do work in this area, so that's one of the things that has been very appealing for me. There are a lot of books on missing data. So I have a book with Don Rubin that's in its third edition. I designed the cover. I'm very proud of my cover, so, which has gone through all the editions actually. But there's a bunch of other things. Rubin's work on multiple imputation, his 1987 book, and then papers, other books as shown on this slide, also give good accounts, I think, of how to handle missing data. And I have a review paper actually coming out in a psych journal, which and also a recent paper with Jim Carpenter and a lady in Australia. Which also I'm going to talk about in this talk as well. So what's missing data? It seems kind of obvious, but it's not quite as obvious as you might think. So to me, the key aspect is that you have data that are not observed in the data matrix. And then the question is whether that would be meaningful analysis if you had that value in there. So missing data are unobserved values that would be meaningful analysis if they were observed. So you have a missed clinical visit in a clinical trial, and so you didn't get the information from that clinical visit. Often that would be meaningful for analysis if you had it, so that would be missing data. On the other hand, if they didn't show up for the clinical trial because they died, then is it meaningful to talk about blood pressure for people after they've died? I think the answer is probably no. So that would be an example that's not missing data as far as I'm concerned. So it's worth looking at the specifics of any particular missing data problem to see whether you think that really is missing data. There are various patterns of missing data. So you could have the first pattern there in A, where missing data is confined to a single variable. That's simple univariate non-response. Multivariate, where you have two patterns in unit non-response in the survey setting, then you often get a pattern like that, because for people for which you don't get any of the survey information, they're missing all the items, but then the others you have them observed. Then there's monotone pattern. If you have I don't know if this is working, this thing, but down if you see my arrow, with monotone data, as you go along the data matrix, you get more and more missing values, and those Y's could be sets of variables. They don't have to be a single variable. That happens, for example, in attrition in a longitudinal study, where you don't have people coming back in. People who are coming back in then destroy the monotone pattern, but often the pattern is prevailingly most of it's sort of attrition. In that case, you get something close to a monotone pattern. And then you have a general pattern of missing data. This is sometimes in the survey world, we call this Swiss cheese pattern because you have holes in the cheese. So a general pattern of missing data. If you have methods that handle general patterns of missing data, then that's probably the most useful. And so in the last 30 years or so, we've got more and more software that will handle general patterns of missing data, which is kind of nice compared to when I was a student, for example. I also put file matching in there. So if you have combining data across data sources, you might have a situation where you have some variables that are common to both the data sources, but then you have some variables that are different in the two data sources. So that gives you the pattern in E, and clearly there's something that you can't sort of estimate from that pattern, so you have to make some kind of an assumption. You can't estimate technically the partial association between Y2 and Y3 given Y1. You essentially have no information about, so you have to make some assumption. Actually, that pattern also comes in the sort of Rubin causal model, the Neyman Rubin causal model, where you talk about Y2, is the outcome if you're assigned treatment 2, and Y3 is the outcome if you're assigned treatment 3. Well, 1 and 2 really. So that actually gives you a pattern that looks a bit like that. Then there's the mechanism. So what do I mean by missing this mechanism? So why a variable is missing, and in particular, are the reasons related to the study variables? That's the thing that really matters. So you have a data matrix D, and you have an observed piece of D, which I'm calling D0, and a missing piece of D, which I call D1. In the first edition of our book, we call this miss and obs, which is sort of convenient, sort of intuitive, but people objected to it for various technical reasons. So this is actually the notation in Rubin's original 1976 paper. So anyway, that's the data, and then you have a missingness indicator matrix, M, which is 1 if an item's missing, and 0 if an item's observed. Or you could have the response indicator matrix, which is sort of 1 minus that. Missing not at random then means that missingness doesn't depend on D. So the distribution of M given D only depends at, no, that's wrong. Sorry, a typo. Distribution of M given D only depends on M. So that should be the probability of M for all D. Rubin calls this dart throwing, data matrix. If the dart hits, then that one becomes missing. I don't know if that's very evocative for you, but anyway, that's what he says. Missing at random, if missingness only depends on the observed values of D. So the distribution of M given D1 is the same. I don't know why I got this thing. Distribution of M given D only depends on D0, the stuff that's actually observed. I think I have to do something about this slide. Apologize. So missingness doesn't depend on things that are missing. So if you know, if you have age, or you have treatment assignment, or you have gender or something, and those variables are observed, then missingness is allowed to depend on those variables. So missingness can vary across treatment groups, for example, because that's a fully observed variable. But you can't depend on, say, the outcome, because that might be missing for the cases that are missing. And then you have missing not at random, where missingness also depends on things that are missing. So that's sort of the most difficult thing to deal with. I'll talk about methods for handling missing not at random later. Most of the methods we have out there essentially assume missing at random. So this is a bit of a limitation. And one of the problems with missing data is often you can't really tell whether things are missing not at random. You can do tests for missing completely at random, but you can't really tell whether something depends on something that's missing, because you only see that variable for the variables for the values that are observed. So in a sense, you can't really test missing at random. So it's kind of a belief or a hope rather than something you can really check. There are methods that do that. So Heckman's selection model for selection bias, for example, does have a test for missing not at random, but that's making other assumptions that allow you to identify the model. What's a good missing data method? Makes efficient use of the available information in the data, is based on plausible assumptions about the missing data, provides valid statistical inferences that take into account the missing data uncertainty. So if you have a confidence interval from the procedure, then that confidence interval has a nominal coverage. If you're doing a hypothesis test, then the test has the right size. That's essentially what I mean by that. In particular, just imputing all the missing values and then analyzing the filled-in data set is probably not going to give you very good statistical inferences because it's going to overestimate how much information you've got. You're basically making up data, and that's not necessarily a particularly good thing. It's a good thing if you don't have enough power to do the study. Just make up another 100 observations and impute them, and then proceed. But unfortunately, that won't have the right confidence coverage. So not very good from a statistical point of view. And then exploits information in the incomplete observations for inference about parameters of interest. For what I'm going to talk about here, the goal is really to provide good statistical inference. It's not necessarily to provide the best estimate of the missing values. In fact, multiple imputation doesn't give you the best estimates of the missing values, but it's basically a method that's designed to give you good statistical inferences. A lot of the machine learning literature that is based on trying to predict things and how well you're predicting things, that's not statistical inference, so it's not what I'm talking about here. Although there are obviously situations where that's an important thing to do. By the way, if you want to ask a question, feel free to interrupt me. All right, so that's preliminaries. Now I'm going to talk about sort of the main approaches that I see for handling missing data, starting with maximum likelihood. I had some very nice chats with folks this morning, and I was talking about I'm writing a book on seminal ideas in statistics, and the first chapter of the book is about Fisher's 1922 paper on maximum likelihood, which is an incredible paper. If you ever haven't read it, it reads like a modern paper almost, except it has some of Fisher's flowery language in there. But aside from that, how many essential modern ideas come from that 1922 paper is pretty amazing. So I'm going to talk about maximum likelihood. So that's a strategy that's essentially analyzing the data incomplete. So it's not actually creating a rectangular data set. You can generate a likelihood function based on the observed data that doesn't require that you have a rectangular data matrix. So maximum likelihood is an example of the thing on the right of this slide. Another example is Bayes, because you can always add a prior distribution and do Bayesian analysis. The other two general strategies is to do imputation to fill in the missing data. I'm going to focus mainly on multiple imputation, and complete case analysis, where you throw out the cases that have missing values. If you throw them out, then sometimes those cases get weighted to make them more representative of the original sample. So maximum likelihood and Bayes are likelihood methods. And the point is that you can write down a statistical model and then throw some data at it and generate a likelihood function. And that data doesn't have to be fully observed. It doesn't have to be a rectangular matrix. It could have missing values. For missing data in general, you need a statistical model, both for the the data, what the data would look like without missing values, the original full data matrix, but also the missingness mechanism. So you have to make assumptions about missingness. And that's not easy to do. So it's nice if you can avoid having to model the missingness mechanism. And most of the software out there for handling missing data, the multiple imputation software, for example, assumes does not include a model for the missingness mechanism. It doesn't ask you how is the missing data related to the variables in the data set. You don't get asked that question. The key point here is that the model for the missingness mechanism is not needed for likelihood inference if the missingness is missing at random, if it's MAR. So that's why MAR plays a very central role in missing data theory. There's a technical distinctness condition between the parameters of the mechanism and the parameters of the data. But the more important of those two conditions, I would say, is missing at random. Why do we like maximum likelihood? Well, maximum likelihood has all those nice properties that you learn in your theory course. It gives you consistent estimates if the model's correct. It gives you efficient estimates. And and you can use inferences based on a normal distribution. So there's a normal approximation. Of course, all this is under an assumed model. So one of the limitations of likelihood inference is that you're kind of assuming that you have the correct model. You can also get standard errors from the observed or expected information matrix, sandwich estimator, or bootstrap, or a variety of ways of getting standard errors. There are three sort of general likelihood-based approaches for handling missing data. There's maximum likelihood, and I'll talk a little bit about software for maximum likelihood in a minute. Or you can be Bayesian. You can add a prior distribution and base inference on the posterior distribution. Or multiple imputation, which in some senses are quite closely related to Bayes. In a sense, for parametric models at least, it's a simulation approximations of doing Bayesian inference. I'll talk more about multiple imputation later. Even though these are likelihood methods and don't really, in a sense, require filling in the data, there are relationships between likelihood-based methods and imputation. And multiple imputation, for example, is an imputation method which is related to Bayes. And similarly, the EM algorithm, which I'm not going to talk about here, has a form of filling in the missing data for maximum likelihood estimation. So maximum likelihood is used in a clinical trial setting quite a lot for mixed model random effects, MMRM type models for longitudinal data. Using programs like SAS, Proc, Mixed, or variance, and there are also methods for non-normal data as well. The programs like SAS, Proc, Mix allow for missing at random missing data in the repeated measures. At least currently, they don't allow for missing data in the covariates. So the covariates, the baseline variables, if you like, are assumed to be fully observed. So that might be a limitation. I think if you had that situation and you wanted to use a program like Proc Mixed, you could fill in the missing covariates using, say, a multiple imputation program and then do the Proc Mixed analysis multiply. There are also extensions to non-normal data like generalized linear mixed models, which I don't like very much, actually, for reasons which I won't explain here. Again, assuming missing at random. Missing covariates might be handled by a method like multiple imputation. This is common in the social sciences. This was originally a talk for an education conference. So I was talking about M+, which is a popular program for doing maximum likelihood. Actually does Bayes as well now, I think, for social science applications. And then there's a lot of quite complex models, multi-level latent factor models that are available as well. And I'm referencing the book by Ray Heskes. There's a good example. So there's quite a lot of software out there for handling maximum likelihood. And then you can do Bayes as well, since there's quite a lot of software for doing Bayesian modeling now. So let me say a bit about Bayes. So add a prior distribution and Bayes inference on the posterior distribution using Bayes theorem. And this was really revolutionized. It was revolutionized by a paper by Tanner and Wong in the 1980s, which they call data augmentation, which is essentially a form of Markov chain Monte Carlo. In fact, it's quite interesting because it's really one of the earliest practical applications of Markov chain Monte Carlo methods to handle a real problem. And missing data is a real problem, obviously. Posterior distribution yields estimates of precision without computing the information matrix, but is also potentially better for small samples because maximum likelihood assumes essentially large samples. So maximum likelihood is really a large sample method, whereas adding a prior distribution can give you better estimates of uncertainty when you have small or moderate samples. And with missing data, it's probably even more the case because the likelihoods for missing data tend to be more complex than the likelihoods for complete data, non-normal, if you like. And many existing Bayesian software packages can be used for Bayesian inference with incomplete data. Again, but most of these things assume missing at random. Actually, the Enders is one of my references more in the social sciences literature. He's a psychologist, but he described Bayesian analysis as an attractive direct estimation competitor to ML. Personally, I think ML is marvelous, but Bayes is better. And why? Well, maximum likelihood is Bayes. It's a large sample Bayes. You're estimating a posterior mode, so it's essentially a form of large sample Bayes. So if you really like maximum likelihood, I would say you're being a Bayesian, you're just being a large sample Bayesian. But for small samples, it gives you better estimates of standard error because it propagates the uncertainty, whereas the large sample standard errors you get in an asymptotic analysis don't necessarily work very well in small samples. And I think that people worry about adding prior distributions to things, that this is more assumptions, but to me, actually, the possibility of incorporating prior distribution is an advantage, it's not a disadvantage, because it conveys a lot of flexibility to the analysis. So I was talking to folks this morning about a paper by Dempster, Vermuth, and Schatzhoff and Vermuth in the 1980s. This is called the 57 varieties paper, which is 57 alternatives to least squares in regression. I don't know if you're familiar with that paper, but it's a great example of an early simulation study, I think. Why do I mention that? Because the alternative is essentially putting a prior distribution on the parameters, and the winner in that particular paper was ridge regression. And to me, ridge regression is just a Bayesian method. So whether you could go the whole hog and I was talking to Raphael about this, whether this is called fully Bayes, and you don't put a prior distribution on. But in most situations, if you're careful about the prior, then adding it probably just makes things better. In terms of inference, in terms of frequentist inference. Okay, so that's likelihood methods. Now, I want to talk a bit about complete case analysis, which is often a default method in statistical packages. If you throw something into a regression package, then what will it do if it has missing data on the covariates? We'll just throw those cases out, right? So it's simple, and it doesn't invent data. So the thing that people don't like about imputation is it's making stuff up. So that seems like it's cheating. So this is not cheating. And And actually, it works okay in some settings. So to me, the important feature is you're throwing stuff out. So is there information in the stuff you're throwing out? If there's a lot of information in those cases, then it's a shame to throw them away. On the other hand, if there's no information there, then why bother trying to use it? Just throw them out. So maybe good enough if the information in the discarded incomplete cases is small. Unfortunately, what's small depends on the setting. So it depends on how much missing data you've got. Fraction of incomplete cases is the obvious thing to look at. How much, what the information is in those incomplete cases, and what you're estimating. So it's a little bit hard to make a hard and fast rule on this. The loss of information from throwing out these cases has sort of two consequences from a statistical point of view. It can lead to inefficiency. If you're throwing away data information, then it's less efficient, but also might lead to bias. And people are probably often more concerned about the bias issue rather than the inefficiency issue. Just as an example of these ideas, here's just a setting where you have missing data on one variable. So Y is the variable that has missing values here. You have a set of fully observed variables x1 up to xp. And let's suppose those predictors were actually a pretty good predictor of Y. So if you were to do a regression, you get an R squared of 0.9 or something. So they're all very good predictors of Y. Then if I was really interested in the mean of Y, if I was in a clinical trial, maybe I'm just looking at one of the treatment arms. So I'm then interested in a mean outcome for that treatment arm. Then Y is missing, but I have some good predictors of Y. So that's a situation where the incomplete cases could have quite a bit of information about the mean, right? Because you can imagine you could predict it pretty well from x1 up to xp, then you might want to include those cases and fill in the missing values of Y somehow. But if you're interested in the regression of Y on the x's, so if you're conditioning on the x's, then there's no information in the incomplete cases. Because if you don't have Y, you don't have anything. If you're doing a regression on the x's, at least on the missing at random. If you're missing not at random, then it's more complicated. But under missing at random, at least there's no information. So if you have missing data and then outcome in a regression, then there's no point in including those cases and imputing them, unless you have some x's that you're not including in the final regression, but are good predictors with missing values. So it depends on what you're looking at. So that's why it's a little bit complicated, but that's the real life. Now in surveys, and we do actually weighted stuff in clinical trials as well. We use methods like weighted GE, for example. Then you take those complete cases, but then you weight them. So, and the main reason for weighting is to reduce the potential bias from complete case analysis. So this is a common technique for unit non-response in surveys. It's the sort of default method, if you like, where it's sort of extending the idea of a sampling weight. So if you have a sampling weight, which is the inverse of the probability of being selected, you sort of multiply it by the probability of responding, or the inverse of the probability of responding, I should say. Trouble is you have to estimate the weight because it's not something that's known like a sampling weight. So there are methods for handling that issue. A couple of approaches is adjustment cell weighting, where you basically classify cases into cells based on variables that are fully observed, and then weight by the inverse of the response rate in that cell. More generally, you could do something called response propensity weighting, where you estimate a logistic regression for the probability of missingness or not missing on the observed variables. and then weight by the inverse of the prediction from that propensity model. And in a sense, adjustment cell weighting is a special case of that, where you have categorical X's. Trouble is, weighting often doesn't work very well. It's something that everybody does, but I'm sort of tending to wager that weighting often makes things worse rather than better. The reason why is for weighting to make things better, you have to have covariates that are good predictors of the thing that's missing. In fact, if they're not good predictors of the things that's missing, then all you're doing by weighting is just adding noise. So you're increasing the variance. So the key thing is to have good auxiliary variables that are predictive of whether you're both predictive of the variable you're trying to impute. Often in surveys, we just use demographic information because that's all we have, and that's not very strongly related to the things we're interested in. So often the method I don't think works terribly well, but anyway, there are some situations where it might be a good thing to do. And then there are extensions. So in the survey world, there's post-stratification, which is using variables from an external source like a census, and weighting based on those variables. And if you have a set of those variables, it's called raking. That's a method in the survey world. You can combine weighting with a prediction method. So augmented inverse probability weighting by Jamie Robbins and other folks at Harvard and other places, where you have a regression model. You get predictions of the missing values from the regression models, but then you weight the residuals from the model, and there are variants of that idea. But essentially, this can can increase the efficiency of weighting by incorporating predictions from a regression. This has what's known as a double robustness property, which means that it sort of works whether you get the regression model for the outcome or a regression model for the probability of response correct. Weighting has a limitation from my point of view, and is that it doesn't really handle general patterns of missing data very well. So can you come up with a weight that handles a general pattern of missing data? I would say probably not. You can do it for monotone data, but doesn't really apply much more generally in that. So usually I think if you're doing weighting for a general pattern, you'll be throwing away some information somewhere. That's why in the survey world, people don't do weighting very much for item non-response. Well, response for particular items typically have a general pattern of missing data, and for that, weighting is not a terribly good method. So what about multiple imputation? So you have a model that creates a predictive distribution for the missing values. You then fill in the data using draws from that predictive distribution, but then do it multiply. So you create a set of, say, M filled in data sets, each with different draws from the predictive distribution of the missing values. The predictive distribution could come from a parametric model, like a multivariate normal model, or from some other kind of an algorithm that gives you a sensible predictive distribution, like the hot deck. Then there are simple multiple imputation combining rules that give you valid inferences under well-specified models. So filling in the missing data with different draws, you can then get your estimate of interest for each of those data sets, and then combine the estimates across the data sets in a way that gives you a better standard error that incorporates the uncertainty from imputation. So multiple imputation is valid, actually, even if the predictive power of the models is weak, since it doesn't really matter too much if you don't have good predictors. You just don't get much additional information, so the variance doesn't go down, but you can still get valid estimates of the uncertainty using the combining rule. The imputation model can differ from the analysis model, and this is a useful thing from my point of view. Often there are variables that might be good to include in an imputation model, but are not necessarily good. What you don't necessarily want to include in a final analysis model. In a clinical trial, you don't want a condition, for example, on post-treatment variables, but you can use those post-treatment variables for filling stuff in, but then do the analysis, leaving those variables out. So that's a useful flexibility, I think, of multiple imputation over something like maximum likelihood or Bayes. There's a lot of software. Again, most of this software is under missing at random. But missing at random, multiple imputation can also be used for missing not at random models, and particularly for a sensitivity analysis, which is something I'll talk about at the end. And there are a variety of approaches for creating multiple imputations, and I've described sort of 3 main approaches here. There's generate a model for the joint distribution, and then typically you'll do a Bayesian analysis for that joint model, and then create multiple imputations as predictions from that model. There's hot deck imputation, which is a sort of more of a survey type method, but essentially creates a match between a case that has missing values and a complete case based on some metric, and then just fills in the values from the complete case into the incomplete case. So the CPS hot deck, current population survey hot deck, was one of the early examples of a hot deck. Then there's the various choices of metric. I don't have time to go into this too much here, but there's predictive mean matching metric that's available in software like SAS, which I think is the best metric for dealing with multiple imputation. So you don't have to assume a parametric model. Hot deck imputation works pretty well if you have a lot of data and you're worried about model misspecification. It's less good for small samples, particularly if you can't get very good matches between the complete cases and the incomplete cases. Then there's sequential regression or chained equation imputation, which is probably my preferred method for doing multiple imputation. I think it's because of its flexibility, and it'll handle a general pattern. One of the early papers on this was my colleague, Raghunathan, who was a student at Harvard, actually, interesting enough, a student of Don Rubin's at Harvard, who did work on multiple imputation. Also, there's mice. Some of you might have come across mice, which is this software that's for doing multiple imputation. That's multiple imputation by chained equations. So that's an example of this kind of an approach. And what does it do? Well, it's sort of a little bit like a Gibbs sampler, but without necessarily but with a flexible choice of the distributions, the conditional distributions that go into the Gibbs sampler. So what do? You take for all variables that have any missing values, you go sequentially through those variables. And so if you have y1, y2, and y3, and you have a set of x's that are fully observed, then you do a sequence where you regress y1 on all the other variables, y2 on all the other variables, and then y3 on all the other variables. In each of those regression, using the most recent draws of the missing values, if those variables had missing values, which sounds a bit like a Gibbs sampler. And in fact, for multivariate normal data, it is a Gibbs sampler. But the idea is that for each of those regressions, you tailor the regression to the variable that you're trying to impute. So if it's a binary variable, instead of doing linear regression, you do a logistic regression, right? Or if it's count data, you maybe use a Poisson type of regression. And then a variety of other possibilities here. So you just iterate around, right, until you get bored or the computer dies or whatever. And then you have multiple imputed data sets that you then do using multiple imputation combining rules. it's very flexible method. The only thing is it's not theoretically clear what it's doing, since this sequence of conditional distributions doesn't necessarily correspond to a joint distribution. So that's sort of a bit of a theoretical drawback. On the other hand, from a practical point of view, then we have difficulty finding multivariate distributions that deal with all these different types of variables. So if you just let that slide and do the thing, then it seems like it works pretty well, provided you pay a bit of attention to each of these individual regressions. So you don't go to something egregious in modeling each of these individual regressions. So to me, the flexibility of the method outweighs the theoretical downside that it's not really a posterior distribution for anything. So I thought I'd talk a little bit about robust methods, and I was planning on giving a talk about propensity scores, which I have a recent paper on that, and there was a discussion at the joint statistical meeting for the Rosenbaum-Rubin paper on propensity. So anyway, this is a use of the propensity in a missing data setting. So the basic idea of this more robust approach is you estimate the propensity to be missing. So this is univariate non-response. You could apply it to a general pattern with some tweaking, but let's suppose you have a single variable y that has missing values. Then do a logistic regression for response, as in response propensity weighting. And then, but don't weight by the estimated propensity. Instead, include the predictions from this, do a regression, where you regress y on the propensity and the other variables. You actually have to drop something out because otherwise things are collinear. But do a spline on the propensity. So you model a flexible relationship between the missing value variable and the probability of response using something like a spline. But then add other variables that are good predictors of y as well. So this is a regression method, but instead of using the propensity as a weight, you're using it as a covariate, as a predictor. And this actually has a double robustness property and is potentially more efficient than weighting, because I'm not a big fan of weighting, probably find out. What about other robust methods? Well, I guess the recent sort of history of statistics has been making up more robust ways of doing regression, right? So you have the lasso, elastic net, and tree-based algorithms, and all that good stuff. Bayesian additive regression trees, which I like, and there's no reason why you couldn't incorporate them and when you're doing model imputation. So the principle still works for these more modern versions of the regression, which might give you more robustness to model misspecification. So when you're doing each of those regressions of for the y's in the chained equation approach, those could be lassos, or they could be elastic nets or whatever. So there's nothing to stop you sort of applying that to the missing data situation. And there's a bit more software that's coming out that sort of does that kind of a thing. I haven't said too much about it here, but I should say a little bit about clinical trials. So let me just confine missing not at random to a single slide and just talk about it rather than going into any detail. So there's sort of a lack of identifiability about missing not at random. You can't really test for missing not at random. And in the last chapter of my book with Rubin, I talk about a variety of strategies for handling missing not at random. One is to get data, so follow up a subsample of non-respondents and incorporate that information into the main analysis, either through weighting or predictions. Impose restrictions on the model parameters that identify the model. And so the Heckman approach, which is which Heckman got the Nobel Prize, essentially an example of that. There are some situations where you can fit missing not at random by selectively discarding data. That's quite an interesting area, but I have a paper with a student of mine that talks about that. But then maybe a little bit on sensitivity analysis. So often we don't really know whether things are missing not at random. And in a sense, the rational thing to do is to look at deviations from missing at random and see how much difference it makes for the thing you're interested in. And that's becoming relatively important technique in clinical trials, because FDA are starting to require this. So and there are a variety of approaches. So the approach that I like is something called proxy pattern mixture analysis, which I don't have time to go into here. But so let me now skip forward a little bit here. I'm going over that method to talk a little bit about clinical trials. So I was involved in this National Research Council report that was commissioned to prepare recommendations for how to deal with missing data in clinical trials, essentially. So FDA funded this. The focus was on confirmatory randomized trials. And in some senses, there's an ICH E9 addendum on estimans, which sort of deals with missing data in a lot of its thing. Some of you are probably familiar with that thing from ICH, the International Conference on Harmonization. A lot of the ideas in that are similar to the ideas that were from this report. The key, sort of, to me, take-home messages from the report: we don't like missing data because it undermines randomization, right? And we all love randomization. We all should love randomization. And so don't have missing data was one of the recommendations, which seems like a fairly obvious thing. But a lot of the clinical trialists on the panel actually felt that people didn't pay enough attention to missing data. And if they did, like monitored it and went to the sites that were doing badly, then they could do a lot better. And I think that's true, actually. In some senses, I think that probably the best thing that came from this report was more emphasis on not having missing data. Also, when you're talking about the estiman, defining estimans, whether you have a lot of missing data in the estiman is important. It should be a consideration, not the only consideration, but should be a consideration. I have a single example on that, which I'll close with. And then do a sensitivity analysis to look at particularly deviations from missing at random in those settings. The idea being, if results are relatively robust, if you tweak missing at random to perturbations from missing at random, then that means that maybe the results are relatively robust as well. So a variety of methods to reduce missing data in trial conduct. I'll skip over that slide quickly, but a lot of it's kind of common sense. But just because it's common sense doesn't mean that people actually do it, right? You all know that. Designed to reduce missing data, run-in periods before randomization, flexible dosage so people don't drop out because of side effects, restrict the trial to the population for whom the treatment's indicated, reduce the length of side effects so people are less likely to drop out, allow a rescue medication to keep people in, and define a population that can be ascertained in a high proportion of participants, for example. And there's more on that. So I want to say a little bit about choice of estiman. This doesn't actually, my example doesn't actually work in cancer, so I apologize. But anyway, I think it's something that's worth thinking about. The estiman is a summary outcome measure of interest defined for the population under study. Alternative choices of estiman may have important implications for trial design and implementation on the rate of missing data. So some estimans may have much more missing data than others. Limiting missing data should be a consideration in the choice of estiman. And one way of doing that is to define what I call an on-treatment summary. The on-treatment summary is a measure of the effectiveness of a treatment that only uses information while individuals are actually on the assigned treatment. One simple approach example of this is treatment discontinuation as failure. Define a binary measure for success or failure and treat discontinuers as failures. That works in some areas, I think. What's the area for pain studies? For example, what's the area under the curve while on treatment? So if they go off treatment, then the area goes down because that's not included as part of the area. But it's only the measure of how much pain has been reduced while you're actually on the treatment. Okay, it's another example. And so on. So try and define something without trying to say what would have happened if they hadn't got off the treatment. Because then you have to decide, well, under what treatment? Under the same treatment, even though the treatment has side effects? Or is it under the rescue treatment, in which case are you really talking about the effect of the drug? So I think there's a lot of problems with trying to impute what happens when people go off a treatment. And so rather than try and do that, instead of defining the thing as some measure of pain in a fixed time point, which might include people dropping out, just measure it in a way that only includes information while they're actually on the drug. It's essentially the idea. I have an example of that, but I'm going to skip over that. Finally, this is a survival analysis setting, so it's not actually in cancer, but I was involved with Janssen on a large clinical trial, was looking at one of the blood thinners, rivaroxaban, for cardiovascular outcomes. And there was dropout in this group, in this study, and the drug wasn't approved. They went back to FDA, so the FDA were mad at them, so because they went back. So they did a bunch of stuff. There are two primary estimands: intention to treat, including all events occurring up until the end of the study, or modified intention to treat, where they only looked at events that happened before the end of the study or 30 days after the last study treatment. So 30 days after treatment discontinuation. The idea being that the effect of the blood thinner would have washed out after 30 days, so it wasn't worth including them. So FDA, of course, wanted intention to treat. Janssen wanted modified intention to treat because there's much less data missing. They ended up doing both. But anyway, this is an example where different types of estimands could have different implications of missing data. And so it might be worth figuring out that it should be taken into account how much missing data. The original analysis, which was by a Cox model, showed a significant reduction in the primary efficacy outcome, which was a composite outcome. Not a lot of dropouts actually in this study, only 5% to 10% dropouts, and with a modified intention to treat estimate, a lot less. Sensitivity analysis was applied to assess the impact of deviations from not missing at random. This is non-informative censoring, or if you like, coarsened at random, using Huygens terminology. So instead of assuming coarsened at random, deviate and allow for a rate of missing data that's higher in the treatment group, and then do a sensitivity analysis. And so you can do these sort of kinds of plots where you say make the deviation from coarsened at random as much as possible until you lose the statistical significance of the treatment effect. So that's what they call the tipping point. So do a tipping point analysis. And to make a story straw for modified intention to treat, it doesn't look like it's very likely that that this would overturn the study. there's not a lot of missing data here. So you have to make the difference between the two treatment groups very extreme before you lose statistical significance. For the intention to treat estimand, there's a lot more missing data, so things are a lot more sensitive to deviations from coarsened at random. And but then I think this is an example of a sensitivity analysis. Kind of shows. So Jansen's way of thinking, of course, a little bit biased. They think it showed that missing data was not the main issue. Yes. Actually, there's an interesting side issue here. The FDA Advisory Committee said that the amount of missing data is the fraction of cases that drop out. Jansen wanted to say it's the fraction of months that are missing, which is a lot less. And actually, I think Jansen is a better measure, because if you look at the fraction of missing information, it's much closely related to the second one. So this is becoming quite prevalent in clinical trials these days. And actually, it's the news is perhaps not as bad as you'd think, because when I've done this, often the sensitivity analysis doesn't make the treatment effect go away, which is, of course, what the drug companies worried about. Often because the deviation from missing at random tends to, if anything, make the treatment effect look bigger for a variety of reasons. The other thing I like about sensitivity analysis is that it reinforces the idea of not having too much missing data. Because if you have a lot of missing data, then the sensitivity analysis might not work out for you for the drug. So I think limiting the amount of missing data in the design and in the conduct is important. All right, so I apologize for going a bit over, but I have a whole bunch of references here. If anybody wants my slides, I'd be happy to send them. But thank you for listening. Can I stop sharing?
Well, we have a couple of questions, so why don't we pull them up, and then maybe you can answer them.
All right. So for mice imputation in a randomized clinical trial, what is the rational approach? Impute jointly for treatment and control, or separately for treatment control in longitudinal studies? Assuming data are missing at random, there are missing baseline covariates and outcomes. Testing both using sample data yield minor differences in confidence bands and standard errors. Yeah. You know, probably doing it separately by treatment group makes sense in a clinical trial setting, because if you try and do it combined, then you're making assumptions that might not be necessary. So I think my short answer would be, in general, it's not a bad idea to do it separately in the two groups. And then should or can any of the methods we discussed be applied to analysis of longitudinal data of data collected in clinical trials of advanced terminal cancer where missingness occurs due to terminal as well as non-terminal events? I think broadly speaking, the answer to that is yes. I think it could be applied. So MMRM, for example, methods, an alternative to that to do multiple imputation. Multiple imputation, you can have more flexibility by including variables that you would not include in the analysis model for the imputation model. But then I'd worry about whether you really have missing data. So do you want to impute blood pressure after people have died? Probably the answer is no. So if you're looking at quality of life, I think quality of life as an outcome only applies to people who are still alive. Which is not to say that death doesn't matter. Obviously, death matters, but it's a separate issue. And please share the slides. Happy to do that. So I can give that to, thank you.
Okay, thanks so much.
You're welcome.